Okay. Hi, everyone. I want to thank the organizer for organizing this beautiful conference. Today, Susana could not be here, so I will give the talk on my own. I'm Nicola from the Institute of Theoretical Physics in Ulm. We are located in this building here in the upper floor. You can see my office here. And today, I want to talk about first simulating open quantum systems and then focusing on electronical dynamics in molecular systems. Let's see. It's not changing the slide. Okay, so simulating open quantum systems. Well, if we want to simulate open quantum system, the goal would be to solve the equations at the core of quantum mechanics that in the density matrix formalism would be the Liouville von Neumann equation. This equation is solidly determined by two ingredients: the density matrix that fully characterizes the system and its dynamics, and the Hamiltonian that describes the energy structure of the system and then its evolution. Even more generally, okay. Oh, now it's working again. We are interested in the case in which the system is not isolated, but is coupled to an environment. So we have to take into account also the presence of the environment, and then we can construct an equation of motion for the system alone by tracing away the environment. So our goal would be to solve this equation of motion for the system, to fully capture its dynamics. And this equation is solidly determined by two ingredients: the initial state of system and environment, and the Hamiltonian model of system and environment. However, solving this equation is very difficult. And here I provide a simple example of it. If we consider a very simple many-body system, which is a system of two-level particles, such as spins, spin up and down, these particles cannot even move in space. So really, for each particle, we only consider 2 degrees of freedom, no more than that, a very simple case. Then if we look at the size of this density matrix, the size of the density matrix will be 2, the number of degrees of freedom per particle, times 2 because it's a density matrix formalism, so 2 to the second. But this for every particle. So the size of the density matrix that we use to describe the system for this equation as it is will be 2 to the 2 to the n. And if we want to store this density matrix on a computer, each of these entries will be a complex number, which will be 16 bytes. So only to store the state of this system of 50 particles that are only two-level systems, we would need 10 to the 22 gigabytes, which is far beyond the computational resources that we have on the planet. And this is commonly referred as the exponential growth problem of the Hilbert space. And this is even worse for open quantum systems where the environment is typically large. So we need to find a way to tackle this complexity. And over the decades, we have found many ways of tackling it, either via approximations or via the usage of different formalism to express the equation of motion. For example, tensor network approaches as a formalism, or approximations such as perturbative expansion of the coupling between system and environment, or finite basic expansions. There are many more. The point is that every of these approximation and formalism and combination of them led to a numerical approach that we use to solve the equation of motion that led to a zoo of numerical techniques that we are currently using to compute the dynamics of open quantum system. Here I just brought some of them. And importantly, each of these methods will be characterized by some maybe regime in which it is valid if some approximation has been done. It might require some assumption of the Hamiltonian. And most importantly, it is characterized by different computational cost. As a rule of thumb, more approximations we do, faster will be the code, which means that if given a finite number of computational resources, faster is the code, bigger are the system that we can analyze. But then it is important to understand for a given process of interest, which level of accuracy do we need? And then which method can we use? And now let us go more on a very specific case. Let us consider excitation energy transfer in molecular systems. Here you can see the FMO complex is a trimeric unit. Each of these monomers contains 8 pigments, but usually in experiments, if this monomer is isolated, one pigment is lost. So there are 7 pigments if we want to compare with experimental results. For this type of systems, so we are interested in electronical energy transfers in molecular systems. We currently have what we call microscopic Hamiltonian models. So we can identify some macroscopic Hamiltonian models that we define as microscopic. We start from the molecular aggregate Hamiltonian, where we model the molecule as a collection of nuclei and electrons that interact with the Coulomb interaction. And then we start performing some assumption, such as the nuclei moves much slower than the electrons. We usually focus on the low energy dynamics. So maybe we consider the first the electronical ground state, the first electronical states, and we consider the motion of the nuclei around equilibrium positions via an harmonic approximation. And with this assumption, we identified this Hamiltonian model. That is the one that is typically used to describe energy transfer dynamics in molecular systems when it comes, for example, in pigment protein complexes, such as the FMO up there. We have an electronical Hamiltonian that simply describes the electronical excited states of each of these pigments, an electronical coupling between the various pigments. But then we have a vibrational Hamiltonian. Each pigment is not a static structure, so it will have some dynamics. And this is modeled as a collection of vibrational modes for each pigment, and a coupling between these vibrational modes and electronical degrees of freedom. Now, there are several parameters that appear in this Hamiltonian model. There are the electronical excitation energies of the pigments. There are the electronical couplings. There is the frequency of the vibrational modes and the coupling to the system. And we can characterize these quantities. For example, the electronical parameters are typically characterized by some first principle methods, such as DFT, TDDFT. And then we have to adjust these estimations based on a fitting between numerically computed absorption spectra or linear spectra and experimental ones. So we can take this estimation and adjust them to match experimental figure of merit, such as linear spectra. On the other hand, the vibrational environments and the coupling to the system can be estimated both with first principle methods, but also experimentally. And these characterizations happens in the form of characterizing the so-called spectral density. The spectral density is what captures the vibrational structure in the environment weighted by the coupling to the system. So it really captures all the relevant environmental degrees of freedom that can couple to the system. The point is that for molecular aggregates, the spectral densities have very similar features, and they are very highly structured. For example, up here, you can see the experimentally estimated spectral density of the FMO complex. It is usually divided in 2 contributions. This yellow part is like a low frequency background that represents more like the protein dynamics, a more dissipative type of environment. But on top of this quasi-continuous background, we have a lot of high frequency peaks that describe the intrapigment modes that are characterized by quite a long lifetime, and that's why in frequency domain they are quite sharp, the peaks. So the experimentally estimated spectral density of the FMO is the sum of these 2 contributions. But here is another example. Here is the PC645, another pigment protein complex participating, performing energy transfer dynamics. And for its constituents, we can see some spectral densities that have been computed with first principle methods, and they are all have the same features. So they have highly structured profiles. The coupling that this spectral density originates have similar amplitude than the coupling within the system, the electronical coupling. So this is a beyond weak coupling regime. And most of these structures are even beyond thermal energy. Thermal energy, even at room temperature, is up here, 200 wave numbers. So we have very rich environments. And this is an issue for, I skipped a slide actually, sorry. Let me go back here, because here I said there is a plethora of numerical tools that we are using that can rely on approximation or different formalisms. But recently there has been a growing interest in what we call numerically exact methods, which are methods that do not rely on any uncontrolled approximation. So are really numerical approaches that can give you the exact solution of the equations of motions. So they are mathematically ensured to give you this type of solution. And these numerical exact tools can indeed lead to accurate predictions. Most importantly, can be used as benchmark for more efficient methods that rely on some approximation. But of course, post that the input Hamiltonian model that we give to this technique has not been overly simplified. So it's a quite accurate Hamiltonian model. And indeed, this type of spectral densities appearing here are a huge bottleneck for numerical exact simulations. And indeed, up to now, in order to simulate energy transfer dynamics in molecular system, until recently, we had to rely on approximations. Approximations either at the level of the environment by the usage of simplified environmental models, such as this red model that you can see here in the figures is a quite smooth spectral density that allowed efficient simulation using one of these numerical tools, that is EOM. Or also we had to use some approximations, either simplified environment or approximations of the equation of motion, such as partial perturbative treatments between coupling between electronical and vibrational degrees of freedom. We will see this later more in detail. Here I'm considering these two references as a comparison between what happens if we impose this simplification that have been used and what if we go beyond this simplification, how much electronical dynamics can change. Because indeed, recently there has been in the last years evidence that these perturbative treatments or simplification of the environment or a combination of the two can lead to very different predictions in the electronical dynamics. And here I can start talking about some of examples. As a first example, taken from this paper from 2022, we consider what happens at the level of electronical parameter estimations. As I said before, the electronical parameters in our models have to be estimated with some first principle method, but then they need to be adjusted by a fitting between simulated linear spectra and experimentally measured linear spectra. And these simulations are quite costly. So up to now, we had to use simplified environmental models, such as this one here in yellow. Here, I'm considering a relatively simple pigment protein complex. This dimeric unit from WSCP is a pigment protein complex that can be found in cauliflower, if I'm right. And this is, so let us consider, this is the spectral density of this complex, very highly structured as the one that we have seen before. This is common for all molecular aggregates. But now if we compute the absorption spectra of this complex, considering this approximated environment, and we match with respect to experimental measured absorption spectra, here you can see in red, the simulated one, in green, the experimental one, then we obtain a fit, but we estimate a coupling, electronical coupling between these two pigments of 70 wave numbers. But now if we start including all the spectral density, we consider full spectral density in our simulations or numerically exact methodologies, considering fully the microscopical model, then we obtain a fit for 140 inverse centimeters, meaning that encoding this structure that have been neglected in the spectral density significantly changes electronical dynamics, and in particular can significantly change our characterization of electronical model parameters. This is the first example that indeed this simplification might have strong consequences on actual electronical dynamics. As a second example, I would like to talk about excitation energy transfer, in particular in the FMO complex up in here. This is the model, Hamiltonian model that we have seen before. And what we refer to as quantum effects in photosynthesis in energy transfer dynamics is the presence of sustained interexcitonic coherences, where excitons are the eigenstates of the electronical Hamiltonian. So in presence of coherences between excitons that are sustained on a picosecond timescale, then we refer to that as quantum effects. Excitons in the FMO, for example, can be delocalized over multiple sites. For example, in here you can see that the lower energy exciton, here highlighted in this gray, is mostly localized on site 3 and 4. Exciton 3 and 6 are mostly localized on site 1 and 2, and they consist of a quasi-dimeric unit, and all the other excitons are roughly localized on other pigments. And in the next slides, I will show you some interexcitonic simulation dynamics, but I will focus on a few of them, in particular, the interexcitonic dynamics between the two lowest energy excitons, but also between these two excitons that consist of a quasi-dimeric unit, because their population can be sustained a bit more, and then if there is some interexcitonic coherences, it might appear also there. As a first example, I want to show a simulation of interexcitonic coherences computed using a numerically exact method and full environment, which means yellow plus blue profile. We take an experimental characterization of the environment and we simulate that. And I want to compare this with simplified models such as this one here, coming from this paper from 2017, where there was a smoothing of this spectral density that enabled simulations of the system at the time. There is a lot of information here. Let me guide through the plots. Up here is the coherence between exciton 3 and 6, and here between the lowest energy excitons, 77 Kelvin on the left, room temperature on the right. Let us start by analyzing what happens if we use the simplified model, so the red and the orange curve. And if we check the data that they generate, we can see that in any case, they quickly decay within 200 femtoseconds, and then they become smooth. There is no oscillation on top of it. So there is no oscillation that is lasting on a picosecond timescale in this case here. But in the moment in which we compute full numerically exact simulations, considering fully the spectral density, then we have the profile in blue and black, so real part and imaginary part of these coherences. And now we can see that there are some sustained interexcitonic coherences. In particular, at 77 Kelvin, there is like a large amplitude oscillation that is proportional to exciton detuning, that at room temperature decays quite quickly. But on top of it, you can see all this high frequency wiggling that is there also at room temperature. It has a timescale of picoseconds. And indeed, it represents some sustained interexcitonic coherences that we will analyze in a moment. Before that, I want to finish the comparison with respect to the simplified models that we used up to now. As a second example, I am considering the simplified model that has been used in this paper from 2020, where the authors consider the spectral density, the experimental estimated spectral density, but up to 500 wave numbers, which is the region where all the excitonic transitions are located. Because at the beginning, we thought that modes that are far off resonant with respect to excitonic transitions might not affect the electronical dynamics. So the authors that I consider indeed the experimental estimated spectral density in the low frequency part, they didn't consider the upper part. And in addition to that, an approximation at the level of the equation of motion. In particular, they considered the electronical vibrational coupling in the exciton basis. They took the off-diagonal path, so the coupling between different excitons mediated through the environment, and they perform a perturbative treatment of it. So perturbative expansion of the interexcitonic coupling. And I here show the same figure of merit as before. So if we consider the red and orange background, plots, we can see that at room temperature, also here, they completely decay within 200 femtoseconds. They remain perfectly smooth, no oscillation on top of it. At 77 Kelvin, there is some oscillation proportional to exciton detuning, but no high frequency wiggling on top that lasts on picosecond timescales. There is not this feature. Which also means indeed that even with this simplified model that has a perturbative expansion of the interexcitonic coupling, but even considering highly structured spectral density, these high frequency components that have picosecond timescales are not present in simulations. And even if we consider full spectral density, but still we consider this approximation, which is perturbative expansion of the interexcitonic coupling, nothing changes so much. So at room temperature, interexcitonic coherences decay within 200 femtoseconds, no oscillation on top of it. So this approximation do not recover this picosecond timescale interexcitonic coherences that are instead included if you do numerically exact simulations considering full environment. And now let us analyze what is the nature of these interexcitonic coherences that we see when we consider full environmental structure. So these are the simulation that we have seen before: coherence between exciton 3 and 6, coherence between exciton 1 and 2, 77 Kelvin, room temperature, considering full spectral density. And in particular, if we look at the spectrum of these long-lived components, so we focus on the dynamics toward 1 picosecond and with Fourier transform, we can see that this is in blue, the frequency spectrum at 77 Kelvin, in red at 300 Kelvin, and in dashed black lines is the spectral density, just as a reference. And we can see that, well, at 77 Kelvin, there are strong components here because still there is this high frequency, this frequency component at exciton detuning that is not suppressed. So we see a lot of frequency components close to exciton transition energies. But on top of it, and even at room temperature, we see a lot of peaks corresponding that follows the structure of the spectral density. And these peaks have similar amplitude to the wave frequency 1. So there really underlies a vibronic mixing between excitons that are at low frequency, but also very far off resonant modes and of similar magnitude. So there is a mixing indeed between these low energy degrees of freedom and all the vibrational spectra, independently on how of resonant they are. And this because there is a frequency-dependent coupling that induces this effect that is typical in molecular systems. Most importantly, these coherences refer to the simulation of one FMO complex. But now we want to analyze what happens if we introduce static disorder. So if we analyze different FMO complexes with slightly different environments that can modulate electronical energies. For example, in experiments, an ensemble of them is analyzed, each of them with slightly different electronical energies, and then the measure that is measured, the figure of merit that is measured as this static disorder implemented. So it's an average over all the possible realization of electronical energies. And here we consider, for example, we focus on the imaginary part of this coherence for simplicity, and we consider several samples over static disorder. So each of these plots corresponds to these interexcitonic coherences computed by slightly varying electronical energies compatible with the magnitude of static disorder that can be inferred experimentally. And what we can see is that the large amplitude oscillation proportional to exciton detuning is different for all of them because we are changing electronical parameters. So this oscillation, of course, is different, which also suggests that if we average over many realizations, this component in this oscillatory component is suppressed. But if we look at the high frequency wiggling on top of it, and we impose an high pass filter, it's perfectly preserved for all of the realization, meaning that these high frequency components that have a time scale of picosecond on a picosecond time scale are perfectly robust against variation of electronical parameters that can be induced by some slightly different local environments. Even more, up to now, these simulations were performed using electronical parameters in literature. But in the first example, we have seen that if we consider full environment, then one has to re-estimate these electronical parameters because the parameters that we are using are based on a matching between simulated absorption spectra and experimental one using some simplified environmental model typically. So like the one that we are using. And indeed, if we simulate absorption spectra using these parameters as we took in literature, here it is in blue, in solid blue line, in solid black line is the experimentally estimated one, and in dashed blue line is the simulated circular dichroism spectra, in dashed black line, the experimental circular dichroism spectra. So you can see they are not a good fit anymore. So we need to optimize these electronical parameters using simulation of absorption spectra and circular dichroism that capture the full environmental structure, so the full spectral density. And this is also what we did. This is preliminary, so it's still rough, but we computed some electronical parameters for the FMO that are capable of giving a better fitting of experiment of simulated absorption spectra and experimentally measured one and circular dichroism. And we wanted to see what happens now at these interexcitonic coherences that we have seen. And indeed, in solid lines, you can see the real and imaginary part of these coherences at 77 Kelvin using the refined parameters in dashed lines using the parameters that we took in literature. So they are quite different. But the most important part is that these high frequency components that we see, if we impose an high pass filter, again, are perfectly preserved, which means that these high frequency components that have a timescale of picoseconds are perfectly preserved, even if we modulate even more the electronical parameters, because the modulation of electronical parameters that we had to impose here are much stronger than the one that we analyzed in static disorder. Here we are talking of a renormalization of electronical coupling up to a factor 2. Okay. Lastly, I want to give some details about two-dimensional spectroscopy. The point is, two-dimensional spectroscopy is the figure of merit that experimentally has been used to probe electronical dynamics in these complexes. The setup is, we have a system initially prepared in the electronical ground state, and then we send 3 time-separated laser pulses. And these laser pulses, they create a lot of dynamics in the system. For example, the first laser pulse can creates optical coherences. This is the electronical ground state. This is the electronically excited state. These optical coherences evolve for a time t1 prior to the second laser. This second laser either promote the dynamics to the electronically excited manifold, where we have this type of excitation energy transfer, or goes back to the electronical ground state manifold. Then this evolves. Then a third laser pulse create again an optical coherences, and then we probe the signal. And experimentally, we have like two-dimensional spectroscopy realizes in these 8 correlation functions. And then on a very schematic and approximate level, what is done, we Fourier transform with respect to T1 and T3, and we define these 2D spectra, where on the x-axis there is excitation frequency, on the y-axis there is detection frequency. So we can see for a given excitation frequency, which energy we detect over time. So over time, this time T2. So we can probe some internal dynamics in the system. And this type of spectra, they give information about the eigenstructure in the system and the transfer between them. So one can probe in the dynamics between different excitonic states, for example. Most importantly, in experiments, one can focus on only few of these pathways, luckily. For example, one can focus on the so-called rephasing pathways that are the 2 highlighted in here. So one can construct the rephasing to the spectra in which only these 2 pathways contributes. But still a major problem is that one obtains a signal where these 2 pathways are superimposed and cannot be discriminated. And in one of these pathways, we have dynamics in the electronically excited manifold where energy transfer dynamics happens and where we have this quantum coherent transport. But the other one is purely vibrational dynamics in the electronical ground state. So experimentally, there is this limitation that if we see some oscillations, we don't really know whether that is a signature of quantum current transport or simply some vibrational dynamics of the nuclei, and then the transport of excitation in the pigment is incoherent. But the key point, let me see here, we did simulation of 2D spectra with numerically exact methods considering full spectral density, but these simulations are quite costly. So for what concerns 2D spectra, we did simulation only considering 2 sides of the FMO. So it's not a simulation of the FMO, but a simulation of a dimeric unit where each of these 2 pigments is still coupled to the full experimentally estimated spectral density of the FMO. So we wanted to see what happens by considering this type of environment. And in particular, we consider a dimeric unit that is similar to the quasi-dimeric unit that appears in the FMO. And even if we consider only these 2 pigments, if we compute energy transfer dynamics, we see similar features. So we see this high frequency component with a lifetime on the picosecond timescale. And then we wanted to see what happens in 2-dimensional spectroscopy. The point is, if one analyzes 2-dimensional spectroscopy with some approximated methods, such as approximation, like a perturbative expansion of the interexcitonic coupling as discussed before, or this simplified environment, one would predict that the signal coming from the electronically excited manifold, that is called stimulated emission signal, quickly decays within few hundred femtoseconds. And the only signal that survives and gives oscillations is the ground state blitzing that is purely oscillatory dynamics in the ground state. But now if we simulate two-dimensional spectra, here is the 2D spectra at time 0. We selected few points, and we follow the dynamics over time of these 2 points. In particular, we can see in blue and in black the real and imaginary part of the signal coming from ground state blitzing. This as oscillation over the picosecond timescale, it goes on. But now we can see in orange and in red the signal coming from the stimulated emission signal, the one that if we use perturbative approaches or simplified environments should decay quite fast. But if we consider full spectral density, the signal has a lot of oscillation on the picosecond timescale is not decaying within a quick small timescale. For example, this timescale t is what if we consider these perturbative approaches, this is the predicted timescale over which this stimulated emission signal should become 0. But you can see that it goes beyond that timescale t. And so this strongly suggests that using simplified environmental model can have a strong impact on electronical dynamics in simulations, and then can substantially estimate the quantum effect in photosynthesis. I went faster than I expected. Okay, we still have 18 minutes, but let's go to the summary. So I hope that I convinced you that one has to be careful when simplifying environmental structure, even in numerically exact simulation. Considering full environmental structure has a deep impact on electronical dynamics, even at the level of estimation of electronical parameters. Then if we simulate in a numerically exact manner with the microscopic Hamiltonian model that we know, that we have constructed so far, electronical energy transfer, we see high frequency components that have oscillatory behavior on a picosecond timescale and that are perfectly robust against static disorder and even a bigger variation of electronical parameters. And then this also suggests in the importance of benchmarking effective, some approximate methods that can tackle way bigger system with numerically exact tools to understand whether these approximate methods can indeed provide valid results. So hopefully then can be used to characterize even bigger results. And the outlook, in the outlook we have that we have seen with this simulation of absorption spectra that we might need a reassessment of electronical dynamics in molecular system inferred by approximated methods. We need a manner of refining electronical parameters that is capable of including the influence of the entire environment, and most importantly, identifying experimental figure of merit for probing the presence of these interexcitant coherences that are not